Hi again, everybody. This time I'm going to do the other topic from 5.1, which is Simpson's rule. You may have learned this in, again, when you were studying calculus. It's one of the commonly used rules, so it's a little more complicated than most. Let me just go through how this goes, actually, because I remember when I saw it in school, nobody explained it to me, and that was a little disconcerting. The basic idea of Simpson's rule is that you do a quadratic interpolation using 3 points of the curve, and then you use that quadratic interpolation to calculate or approximate the area under the curve, subtended by those 3 points. So here's a simple example. We have 3 points from some curve, and we're going to form the quadratic interpolation. Or we could assume that the function given is quadratic, and we'll just compute the area under the quadratic curve that passes through those 3 points, right? So up here, let me see if this is working. Here's where I've got the picture, right? So we got the 3 points here, here, and here, and then we have the curve that represents the quadratic interpolation of those 3 points. And we want to find the area under the curve. So I've divided that area up into 2 pieces. One is a rectilinear piece, actually a trapezoidal piece, right? And we know how to calculate that area. And the other, the yellow part, is that piece up there. And that will be the extra part. So in a sense, this is like taking the blue part, which is the trapezoidal method, and correcting it by adding the yellow part from the quadratic interpolation, right? That's basically what's going on. So the linear part is really easy to do. Oh, by the way, I'm assuming that the 3 points are located at x equals a plus h, and x equals a plus 2h, which I'll also call b, okay? And then the area, the blue area for the trapezoid is simple. The width of the trapezoid is 2h, and the average height is the height at a and the height at a plus 2h, right, divided by 2, right? So the average height, and of course the 2's cancel, so we get this formula for the area of the trapezoid. Then we also have to compute the area of that little dome, that little yellow dome above the trapezoid. So this piece here, and I'm going to let alpha be the difference in height between the midpoint of the straight line at the top of the trapezoid and the peak at the of the parabola at that same x value, right? So it's the difference in height at the middle, at the point x equals a plus h. So I wrote out over here that difference in height would be that the height at a plus h is f of a plus h. The height of this linear interpolation between the 2 points would be just the average of the heights at a and at a plus 2h. So this is f of a plus 2h divided by 2. So I'm calling that alpha. Alpha is the difference in height between the parabola and the linear interpolation at the center point. Okay, so now how do we find the area of the yellow area of the quadratic area? So that's over here. So I did that in brown over here. This is the calculations for finding the area of the yellow part of the quadratic part. And by the way, you can simplify the diagram. It doesn't really matter whether the bottom is slanted or not. If you have a parabola that has the same height at the center point, it's going to have the same area. So I've just flattened it out so that I'm going to say that that yellow area, or that yellow curve, we can assume is simply this. So this is a simple quadratic function, which you'll notice is 0 at a because it contains the factor x minus a. It's also 0 at b. And when you plug in a plus h, then this term becomes h, this term becomes minus h, And therefore, h times minus h is minus h squared, and therefore this term becomes 1. And therefore, if we just multiply it by alpha, this function here will take the right value, alpha, at the point a plus h. Okay? So, so the area under this curve will be the same as the area here between the parabola and the linear interpolation. So let's compute the area here. Just for practice, keep you sharp, I'm going to do it by integrating by parts. So I want to integrate this function from a to b. And I'm going to integrate the x minus b term first. That gives me x minus b squared over 2. And everything else goes along for the ride, and we evaluate that between a and b. And of course, when we do that, everything becomes 0, right? When x equals a or when x equals b, it just becomes 0. The other part we have to do is we have to subtract off what we get with the integrated term multiplied by the derivative of the other factor. Now, the other factor here that I didn't integrate was x minus a. Its derivative is 1. So I have to subtract off x minus b squared over minus 2h squared. The minus signs cancel. I just canceled them here, so I just wrote it as plus and positive 2h squared in the denominator. And now this we can just do, this is really just a second power. If you want, you can think of it as a substitution, u equals x minus b, but the integral is simply x minus b cubed over 6h squared times the constant alpha. And when we evaluate that between a and b, well, at b, of course, you get 0. At a, you get a minus b, which would be negative 2h. So, yeah, negative 2h squared would be negative 8h cubed. We're subtracting that off because this is the value at the lower limit, so that's why the sign turned out to be positive in the end. Right. And therefore, when you simplify the whole thing, you got 8h cubed over 6h squared. It reduces to 4/3 h times alpha. Okay, so that's the area of the yellow region up here. So if I add those two up, under the quadratic interpolation, the area becomes, let's see, the linear area here plus the quadratic area there. Everything's multiplied by h, right, up front. Now, when you plug back in the value of alpha, remember alpha was this, it was the difference between f of a plus h minus the average value of f at a and at a plus 2h, and do the algebra, simplify things, it comes out to be this at the bottom here. So this is our formula for the area under a quadratic interpolation of a function where we've sampled the function values at the 3 points a plus h, and a plus 2h. And notice, kind of interesting, the middle point seems to count for a lot more than the two endpoints. I guess that makes sense, right? The endpoints, after all, they only affect the values of the function on one side, or either the left side or the right side, whereas the middle point has kind of an influence on both sides. But it's interesting that it's actually 4 times as important as either the left endpoint or the right endpoint in calculating the area. Okay, so now I'm going to take this formula here, and I'm going to apply it to a numerical integration method. Right? So the problem is we want to find the area under this curve. So this is a curve where y equals f of x. And what we're going to do is we're going to sample it at all these points from a to b at intervals of h, right? So first at a plus h, at a plus 2h, and so on, all the way until we get up to b, which is going to be a plus n times h. So n is going to be the number of these subdivisions that we use. Notice, in order to use Simpson's rule, n has to be even, because we have to, we need 3 points to apply Simpson's rule. So therefore, we need to combine 2 of these segments together in order to use the 3 points that they provide in order to apply Simpson's rule once. So we'll apply Simpson's rule once here, and then we'll again apply it on the next two segments, and then again on the next two segments, and then on the next, and so on. So we're applying Simpson's rule in pairs like that. And so what we get is that the integral from a to b of f of x is going to be equal to, and now I'm going to apply that formula. Remember, there was a constant factor of h over 3 out front in front of everything, so I got that here. And then what do we do? Well, the first endpoint counts once, as we saw here, right? The first endpoint just counts once. The second point counts 4 times. So I got this counted 4 times. Then we come to this point here, and that counts once for the left 2 intervals, but also once more for the right 2 intervals. So that's why I've actually counted it twice. And then it's going to alternate from then on. The next one will be this one here. It's going to be in the middle of this pair of intervals, so that's going to count 4 times. And then the next point here is going to count twice, once for the left and once for the right. And so on. It's going to alternate between the weights of 2 and weights of 4, until finally at the very end, we get one that just counts once because it only counted as a right endpoint. So, right, so what this basically boils down to is that we're going to count the extreme outer endpoints A and B once. We're going to count the even indexed points 4 times, and we're going to count the odd indexed points. They're each going to count 2 times, right? Now, we're going to try this out on the computer. I had a little extra space here, so I thought I'd work out the numbers we can use to check our answers. If we integrate, I want to integrate some simple polynomials to just the powers of x. So if we integrate x squared from 0 to 2, as we did in the previous video, we get 8/3, which is 2.66 repeat. If we integrate x cubed between 0 and 2, the antiderivative will be x to the 4th over 4. If you plug in 2, you get 16 over 4, so that's exactly 4. And if you integrate x to the 4th from 0 to 2, the integral is x to the 5th over 5. If you plug in 2, you get 2 to the 5th over 5, which is 32 over 5. It's exactly 1.6. Okay, so we can use those values to check our answers when we run the computer function. Let's see, so here's the computer function. Once again, what have I done here? Huh. I seem to have forgotten to rename the function. That's weird. But I was supposed to have renamed the function Simpson f. Let's see, so I should have said this would be Simpson, underscore f. And for some reason, it just says Simpson. So Atkinson's version was Simpson, and the last argument, again, it was not a function, so I just rewrote it slightly to change that. The overall structure of the program is exactly the same as the one for the trapezoid method, so I'll just show you the differences. In this case, for the Simpson integration, we have to keep track of the values of the function at the extreme ends at A and B, just like we did for the trapezoid method. But in this case, we have to distinguish between the odd sample points and the even sample points, right, when the indices are even or odd. And one thing that's nice about this, though, is that here, if you look at the picture over here, you can see that if we're currently looking at these sample points, at the blue and yellow sample points, then you can see that this one's odd, this one's odd, this one's odd, this one's odd, and the yellow ones are even, right? Even, even, even. So they get weighted differently. However, when we double n, when we subdivide all those intervals in half, then all those yellow and blue points now become even intervals for the next n. So therefore, down here you have this point in the iteration when you take the previous odd and even ones, add them together, and they all become together the current even nodes. Okay? And then finally, he applies the Simpson's rule, and it takes h over 3 times the values at the sum end, 4 times the values at the at the odd nodes, and yeah, and 2 times the values at the even nodes, right? Let's see, did I do that right before? Yes. Right, so these would be the odd nodes, and these would be the even nodes. Right? So let's see. Let me try color coding them. How about this? These are the odd nodes, and these are the even nodes. Right? The two. So even nodes here, and odd nodes there. Right. Okay. And now. So right. Okay. And then he does the same thing. He computes the integrals for various different values of n, doubling the value of n each time, and then compares them all by looking at the differences and the ratios between the differences. Okay, let's switch over to MATLAB. Okay, let's see, let me clear the screen, pretend I haven't done anything yet. Let me see. Oh yeah, Simpson F. Oh, I see. Maybe I was looking at I was looking at the documentation for the function where I hadn't changed the name Simpson F. So, but I did call the function Simpson F. Okay. So let me do the same thing I did the other day. Let's first of all, let's set the format to be long so we can see everything better. And next, let's define a function. I'll tell you what, let me call F2, I'll call out the quadratic function x squared. Let's do F3 to be the cubic function. And let's say F4 is the quartic function. Oops, left out a parent, okay. And then we'll try applying Simpson's rule. Oh, by the way, it might also be interesting to compare Simpson's rule with the trapezoidal rule. So why don't I do that? Let's see. So I want to keep track of the values of the integral for the different ends, the differences between them, and the ratios between the differences. And let's try it first with the trapezoidal rule, which we did the other day. Let's go from 0 to 2. And I'll tell you what, to make this fair, let me start with two iterations. I think the other day I did one, but I'll start with 2 intervals because you need at least 2 intervals. You need an even, as I said, you need an even number of intervals to apply Simpson's rule. So just so they're both, I can compare apples to apples here. I'll start them both off with 2 intervals, and let's do the x squared function, the quadratic function. Okay, oh, there we go. So this is pretty much, well, it's pretty much what we got the other day, except they're one step ahead because the other day we started with 1 subdivision, here we started with 2, right? But you notice again that you've got all these 4s, right? That the ratio between successive differences is always 4, like we saw the other day. Let's try it with Simpson's rule. Let's see, you might want to think for a second, what do you think will happen if we do it with Simpson's rule? Oh, that's interesting. What happened? We got the right answer immediately, right? And that should have been expected if we thought about it, because after all, Simpson's rule is based on doing a quadratic approximation. If the function is quadratic, then the quadratic approximation is exact, and we get the exact answer immediately, right, without having to even iterate. So yeah, so that's not actually surprising. Okay, let's see what happens with the cubic function. So let me go back and do the trapezoid. Let me do it with F3. Remember, the correct answer was supposed to be 4 for the cubic function. Okay, so the trapezoidal method for the cubic function, it does eventually give us a very good approximation for the correct value, right? It starts out with an approximation of 5, but it gets up close to 4. Notice again, we have the same pattern that the ratios of the differences are 4 consistently, uniformly. What else? Okay, let's try this with Simpson's method then. So, oops, Simpson. Oh, that's interesting. We got 4 again immediately. We got the right answer immediately. We didn't have to do any iterating. So interesting. Why is it that when you do a quadratic interpolation or quadratic approximation of a cubic curve, that you get the exact answer immediately without having to do any iterating or just subdividing the intervals into smaller pieces? That's interesting. I'll come back to that question. That's an interesting, it actually turns out to be a quite general feature that in fact, Simpson's method is exact not only for quadratic functions, but also for all cubic polynomials. Okay, now let's try it with F4. Okay, remember the value was supposed to be 6.4. So again, the trapezoidal method works well. We do get the value of 6.4 eventually, right after it comes out to be accurate to like 5 significant digits after 9 iterations of doubling the number of intervals. Once again, you can see that the ratios between the intervals are all essentially 4. It's not quite as pretty it was in the previous 2 examples, but it's still essentially 4. So the difference is reduced by 4 with each iteration. Okay, now let's try it with Simpson's method. Let me do F4. Oh, that's good. Okay, so Simpson's method worked better. Notice that we actually got Simpson's method was accurate to 5 significant digits, almost 5, not quite, but almost 5 significant digits by the 4th iteration, whereas the trapezoidal method required 9 iterations. So it does seem that the Simpson's method works better and faster, and if you do it for 9 iterations, you get it to much greater accuracy, right? Much more significant digits. Another thing to note, notice that the ratio between successive differences in this case is 16. So again, using the basic principle that the difference between successive iterations, the difference in the estimate between successive iterations is also a good estimate for the error. We would expect that the error is also decreasing by a ratio of 16 at every iteration. So again, what we're seeing is that Simpson's method seems to converge much faster than the trapezoidal method, right? And that's why it's favored by numerical analysts. Let's try this one more time with maybe the 5th, a quintic function. So x to the 5th. And see if the same thing holds, and see if the ratios between the differences are still going to look like all 16s. Oh, what was that? Why did that happen? Okay, there we go. But yes, it did. Same thing. We didn't work out what this answer was, but you can see that the ratios between successive differences are still going to be 16. It looks like the correct answer is 10 2/3, right? I'm willing to place a bet on that the exact answer to this question is 10 2/3. Okay, so now let me go back to the question I raised before. Why is it that Simpson's method gives the exact answer not only for quadratic functions, but also for cubic functions? Okay, let me go back to my notepad. Okay. So here's the thing. Suppose you want to calculate the integral of the cubic function from a to b. So I'm just doing the simplest possible cubic function here, x cubed, right? Let's integrate x cubed from a to b. Now, what I'm going to do is I'm going to transform the integral from a to b to the integral that we used earlier when we were looking at polynomials. When we were studying polynomials carefully, we found it was helpful often to change to the interval from -1 to 1. And that was a good way, actually, of analyzing polynomials to think about how they behave on that particular interval. So I'm going to do that here. I'm going to transform, I'm going to make a change of variables so that the integral goes from, instead of going from a to b, it'll now go from -1 to 1. So what I do is I'll let m be the midpoint between a and b, a plus b over 2. I'll let r be kind of the radius of the interval from a to b. It's the distance from the midpoint to each of the endpoints, right? So b minus a over 2. And then we can do a simple transformation where x equals r times u plus m, where u is going to be the new variable. If we need it, u is actually equal to x minus m over x. Actually, I don't think that matters. But then using this, we can obtain the relationship that dx is equal to r times du. Right? So that's what we need in order to make the change of variables. So therefore, if I replace dx by r times du, a under this change of variables goes to -1, and b under the change of variables goes to 1. And x, of course, becomes ru plus m. So the integrand becomes ru plus m. Now I'm going to expand this cube here. We get r cubed u cubed plus 3 ru squared m plus 3 ru times m squared plus m cubed. Right? You remember how to expand a cube, a third power of a binomial, right? Now here's the thing: if we're working on this interval from -1 to 1, you'll recall that all the odd terms disappear when you integrate, right? Because when you integrate an odd term, in this case, we're integrating with respect to u. So if you integrate u cubed, you're going to get u to the 4th over 4. But u to the 4th, because it's an even power, takes the same value at 1 as it does at -1. And therefore, when you subtract the values of the two limits, they're going to cancel. So these odd terms, when r is 3 and when r is 1, they disappear. And therefore, the whole integral is simply becomes equal to the integral of the quadratic part, right? It actually reduces to a quadratic integral, or the integral of a quadratic function. Now, it shouldn't be surprising that the integral of a quadratic function can be calculated using Simpson's rule, right? We would expect that. The point is that despite the change of variables, that isn't going to confuse Simpson. Simpson can handle that. And Simpson can tell that, in a sense, that the integral is really, in essence, only a quadratic function, and therefore it does return the correct value, even though we're using a quadratic approximation on a cubic function. Right? So cubic function, we used a quadratic approximation, but we get the exact answer because, as it turns out, the function, in some sense, the integral was essentially only a quadratic function, the integral of a quadratic function. Okay, so that's nice to know. It means that Simpson's rule will be exact not only for quadratic, but also for cubic functions in general, right? So by going to the trouble of making quadratic, the quadratic interpolation, quadratic approximation for free, we got an extra degree. We got all third-degree polynomials calculated exactly for free. Right? That's a nice feature.